Hello and welcome to this talk. I'm going to talk about the approaching zero template overhead and about template overhead in general. There will be datasets and there will be a few numbers shown during this presentation. There will be a small demo part which I recorded earlier that refers to the template problems that I found in RDMB. And without further ado, let's talk a bit about me. Well, you can see me, that's me. I'm Stefan Koch, and I'm a compiler developer person since 2014 when I started on STC, and later on I got into working with DMD. And I've been working on projects to improve the compile time performance, and this talk is a bit about that as well. So we have a compile time problem. We have compile time performance problems, and they are quite large. We at Symmetry, we have machines. We have machines for our developers which have more than 128 gigabytes of RAM, right? And part of that is because that what the build needs, when we build our project, we need, I think it was 16 for a regular developer build, and for a build that passes the whole CI pipeline and builds everything, you need more than 30, which means that the next power of 2 is 32. That's usually not enough because Chrome will take up more than 2 gigabytes. So then you have to go up to the next power of 2, and that's 64. And that sometimes works, sometimes it doesn't. So to be safe, we have 128 gigabyte RAM in our developer machines usually. And that is, of course, it's of course possible, right? Since now you can get these sizes, but still, I think if I told anyone that the compiler I'm working on takes 128 gigabytes of RAM to compile a big to medium sized project, you would think that's crazy, right? So let's go into what this problem is. The problem is that the Symmetry codebase and the Weka codebase, they suffer from the same problem, are fairly template heavy. They generate a lot of code. That means most of the code is not actually written in the file. It gets created during the compilation process, and when you use templates to do that, you tend to generate a lot more code than you would think you do. Let me very quickly talk about the concept of the expansion factor. The expansion factor is quite easy. When you compile code, for example RDMD, then the code that you see here is not all the code that's getting compiled. And the way you can get at all the code that's getting compiled is you use a switch called a view codegen AST. and I've built a little script that that takes care of using VCG-AST to create the expanded script and then computes the expansion factor. So if we run the expansion factor on RDMD, what we see is Koch considers RDMD to have 760 lines, and the expanded version of RDMD has 11,000. Not good with numbers, so yeah, it has 119,000 lines, which is an expansion factor of 157. So rather than having roughly 1,000 lines to deal with, you roughly have 100 times that to deal with, and that's the reason why compiling RDMD takes over 2 seconds. And when you look at the symmetry code base, parts of the symmetry code base have blow up factors that are over 500x. So that means you will see 1,000 lines of code, but actually you're compiling 500,000 lines of code, which is like 2 orders of magnitude higher. So all of that code, of course, needs time to be compiled. The compilation performance of DMD is mainly dependent on how much code you feed in. And that is not only the source code that you feed in, that is also the code that is generated while you are compiling the program. So, what's the solution to that? You can already read it on the slide, so it's not a big question. Generate less code, right? Because compilation performance is mainly determined by how much code the compiler has to process. That includes lexing and parsing, so that is in modern projects which generate most of the code, that is a completely negligible time that you take for parsing and lexing. It used to be the most important thing in a compiler, that it has a fast parser and a fast lexer, and in languages which do not generate code at compile time, that is still the case. However, as soon as you support templates or any other dependent typing mechanism, you will run into this situation where the code that you see on the page is not even close to what the compiler actually has to deal with, because templates are code generators. So I thought I had another slide, but let's wing it without. So templates are code generators. A template actually does nothing but produce code, right? When you write a template, what you do is you basically have a macro, but it doesn't use text replacement. It replaces AST nodes. So a template can be seen as a heavily constrained AST macro, and usually a quite poorly implemented one, because templates, well, they're just meant to be used as actual templates. You have a block of code that is parameterized on a type or on a function maybe, and then you want to copy that code, paste the type in, and create a new instance which is then specialized for that type. And that is what templates were originally meant to do, and they're fine when they're doing that. However, when you use templates to do something that is not that, for example, if you use templates to do this, if you use templates to create a series of numbers, well, from a series of types, then as you do in here, traditionally you have to use this recursive approach, right, where you feed something in, you pull off the first template argument, and then you recursively instantiate the template with the rest. That works, but despite being syntactically ugly, it's also not very efficient at compile time, because you can't do things like loop unrolling, since you do not know how long your template parameter sequence is. You only check if it is over yet, and if that's not the case, you check if it has only one member, and then you instantiate the function, and then if that is not the case, you call it recursively, and that means that you cannot see through this, right? To the compiler, this template is completely opaque. All it can do is replace the template arguments, like that, is then replaced into here, and then the regular semantic is being called on it, and that then recursively instantiates this template, and through that you can support transformations or computations on types without giving the compiler an actual understanding of it by abusing this template macro system. And that has unfortunately gained a lot of fellowship, and it is now common practice to do these things, but it is really not trivial to make this performant, since you do not have any information about the control flow that happens. You're really just expanding a pattern, and you have to finish expanding the pattern before you can tell when you would have to finish, right? So you just expand that sequence over and over until you hit one of these termination cases, and that's basically it. And that's why it is quite hard to make this fast. When we compare this with the dot version that has a built-in expansion, so this also just expands the pattern. What happens with ... it takes byte, u short, u int, u long, the sequence of types. It puts it in here, and it sees that there's a sequence, a so-called tuple. And then it looks at the operator or anything that is applied on that sequence. When the ... operator happens, it sees that, and it will replace it with another sequence that then is byte, size of, u byte, size of, u short, size of, int, size of, and so on, which then becomes a sequence of 1, 1, 2, 2, 4, 4, 8, 8, 1, 2, 4, 8, and then it that sequence, because it is written inside the brackets for an array, it will be put into the array literal, and we can compare that these array literals are actually the same. And because this uses a built-in expansion functionality without relying on template abuse, that can actually be quite a bit faster, as we will see on the next slide. Right, here we can see that when we use it on a fairly long sequence of types, like the type sequence that we saw before, with where most of the basic types are in, and we compare how static map and phobos performs and how the ... expression performs, we will see that the ... expression is roughly 1.6 times faster than the static map, and the static map only works because it has been rewritten to use less template instances. I think we will see that here. Yeah, we'll see that here. A phobos version is written to avoid recursive template instances. What it does, it uses string mixins, which unfortunately is still the most performant way of metaprogramming. So that means our template and AST macros have a significant overhead when compared to basically textual inclusion, which is what a string mixins provide you with. So, if it is 1.6 times faster, should we use ... everywhere? Well, as you can see on the slide, it's a dip which is in progress, and it's not yet approved. And there are use cases, especially if you use static maps within static for eaches, where it is much slower than using the version that's currently in phobos, right? Which again is based on string mixins. It tries to avoid templates wherever it can, and that is where we are at. So in the cases where the ... expression is faster than the phobos static map, it is faster because it does not generate intermediate results, intermediate ST nodes. Rather, it tries to do an in-place expansion. Now, because of certain order dependencies inside the semantic system of DMD, those also involve copies, and they're not always faster, but when they are faster, they're faster because of that in-place expansion. They don't cause additional template instances to be generated, and therefore they cause less code to be generated, and therefore faster compilation. That is something that you will see all the time. Less code means usually faster compiler. And I'm not talking about the code on the page. I'm talking about the code that the compiler actually has to deal with. And that's why it is an important difference whether you use a library functionality that is provided via templates, or whether you use a built-in functionality that is provided by basically me spending time and implementing it and making it fast. And the other thing is that dot is really just a replacement for expansion. It is written to be simple as it can be, and it can only do straightforward mappings and straightforward reductions. And I don't actually have that many use cases for the reducing operations that can be done with straightforwardly just applying one operator, but therefore I don't have examples for it. But I know that there are some people who quite like to have it, and maybe that could help them. And apart from dot, we also have future options, and those are, for example, type functions or alias assignment. And unfortunately, those are not complete or functional enough that I would include them here because of the reproducibility aspect that I have for this talk. I want all the things that you see should be reproducible for you. Right? You should be able to do those measurements on your own code and see what they say, and then see where you could have compile time performance improvements, or if you can't have any. Let me talk about those two things, type functions and alias assignments, nonetheless. Type functions follow a very simple idea. They just say, when you can execute a function at compile time, why not execute a regular function on compile time entities? Because the interpreter is built into the compiler, it has access to the AST. So rather than implementing a separate AST macro system, what you can do is write a regular function that takes types of functions as input, which is then evaluated at compile time and can give you types, functions, or other symbols back. Right now, it's rather restricted because of forward reference issues in the compiler, which is also something that plagues dot expressions and basically all extension attempts where we try to get more expressive and more efficient metaprogramming. However, those are really for a separate talk. You can contact me privately if you want to talk about it, and maybe I will in the future also release some YouTube videos on the topic. Now, I am afraid that is it. And one more thing, Symmetry Investments is currently hiring. We're looking for talented people from all backgrounds. Formal qualifications are not a requirement. I myself do not have a university degree, and still I'm working for Symmetry on a fairly advanced project. So if you're interested and if you think you can contribute anything to us, go to symmetryinvestments/careers, and I will be happy to greet you as my new coworker.